Sending signals into space is a bit like shouting across a huge, empty field. If it's quiet, your friend might hear you. But what if there's a giant, roaring concert happening right next to them? That concert is our sun. The sun is a star, and it's incredibly bright and loud in terms of light and energy. It floods our planet and the space around it with so much sunlight that it can easily drown out the faint signals we try to send from Earth. This is why, for many years, scientists could only do certain kinds of sensitive space communication at night, when the Earth's shadow gives us a brief break from the sun's overwhelming glare. Imagine trying to see a tiny firefly blinking next to a giant searchlight. The searchlight's powerful beam would make the firefly's little light completely invisible. The sun acts like that searchlight for our messages to space. The signals we send, even powerful ones, are like that tiny firefly. By the time they travel thousands of kilometers to the moon, they are very weak. The sun's constant stream of light particles, or photons, bombards our detectors and creates a lot of background noise, making it almost impossible to pick out the specific faint signal we are looking for. It's a fundamental problem for anyone trying to talk to satellites or rovers. This solar interference is the main reason that precision work, like measuring exact distances to objects in lunar orbit, has historically been a nighttime activity. Scientists would wait for the sun to set, giving them a clear, dark cosmic canvas to work on. This limits when they can track satellites, get data, or communicate with missions. If a rover on the moon needs urgent instructions during the lunar day, waiting for nightfall on Earth isn't always practical. Finding a way to overcome the sun's daytime noise has been a major goal for space scientists for a very long time. Solving this puzzle means we could have constant, around-the-clock communication and tracking for our space missions. It would be like being able to use your phone anytime you want, instead of only after the sun goes down. For ambitious goals like building a base on the moon or having people live and work there, you need a reliable connection that works 24/7. You can't just shut down operations because the sun is up. So the challenge was clear. Scientists needed to find a tool so powerful and precise that its signal could cut through the sun's noise and be seen, even in broad daylight. So how do you send a signal that won't get lost in all that sunlight? You use a laser. Think of a regular light bulb. It sends light out in every direction, spreading out and getting weaker the farther it goes. A laser is completely different. The word laser stands for light amplification by stimulated emission of radiation, which is a fancy way of saying it's a super-focused, super-organized beam of light. Instead of spreading out, laser light travels in a tight, straight line. All the light particles march in the same direction, like a perfectly disciplined army. This focus is what makes a laser so powerful and perfect for space. Because a laser beam is so concentrated, it can travel incredibly long distances without getting too faint. It's like using a laser pointer to make a tiny red dot on a wall far away, while a flashlight beam would just be a dim, wide circle. When we point a laser at the moon, that focused energy helps it stand out against the messy background light from the sun. Scientists can also tune the laser to a very specific color or wavelength of light. This allows them to build special detectors on Earth that are designed to look for only that exact color, helping them filter out all the other random light from the sun. This technology isn't entirely new. Astronauts on the Apollo missions, back in the 1960s and 70s, left special mirrors, called retroreflectors, on the moon's surface. For decades, scientists on Earth have been bouncing lasers off these mirrors at night to measure the exact distance to the moon. By timing how long it takes for the laser light to travel to the moon and bounce back, they can calculate the distance with amazing accuracy. This technique is called laser ranging, and it's one of the best tools we have for measuring things in our solar system. It's a cosmic ruler made of light. However, using that cosmic ruler during the day has always been the ultimate test. The returning laser signal is unbelievably weak. We are talking about just a few photons or particles of light, making it back to the detector on Earth. Finding these few special photons in the massive flood of photons from the sun is the hard part. It requires incredibly sensitive detectors, powerful filters, and a laser system strong enough to make its mark. It's this combination of a powerful, focused beam and smart detection technology that gives scientists a fighting chance to beat the sun. In a major breakthrough, scientists in China did exactly that. They won the battle against the sun's glare. Between April 26th and 27th, 2025, a team from China's Deep Space Exploration Laboratory and the Yunnan Observatories of the Chinese Academy of Sciences conducted a groundbreaking experiment. From a station in Yunnan, they aimed a powerful laser not at the moon itself, but at a special satellite orbiting the moon. This satellite, named Tiandu-1, was specifically designed for this kind of work. It was launched in March 2024 to test new technologies for lunar navigation and communication. For this experiment, the team used an upgraded 1.2-meter telescope that was equipped with a special near-infrared laser system. The laser beam shot out from Earth, embarking on an incredible journey through space. It traveled approximately 130,000 kilometers, that's about 80,000 miles, to reach the Tiandu-1 satellite, which was about one-third of the way to the moon. Think about that incredible distance. The satellite, which is quite small, caught that beam of light, and thanks to its onboard retroreflector, bounced a tiny fraction of that light right back toward the telescope in Yunnan. All of this happened in broad daylight. The reason the team was so determined to try this during the day is all about availability. As mentioned before, future lunar missions, especially those with astronauts, will need constant support. You can't tell an astronaut who is having an emergency on the moon to wait 8 hours for the sun to set on Earth so you can get a good signal lock. Proving that you can accurately track a lunar satellite anytime, day or night, means you can provide non-stop navigation and communication. This makes future missions safer and more efficient. It's a critical step toward having a permanent human presence on the moon. The most amazing part? It worked. The team on the ground successfully detected the faint photons that made the round trip from Earth to the satellite and back again. This was the first time in history that anyone had achieved laser ranging to a satellite in lunar orbit during the daytime. Not only did they get the signal back, but they did so with unbelievable precision. They were able to measure the distance to the Tiandu-1 satellite with centimeter-level accuracy. That's like measuring the length of a football field and getting it right down to the width of your pinky finger, but from 130,000 kilometers away. This incredible achievement is more than just a cool science experiment, it's a game changer for the future of space exploration. Achieving centimeter-level accuracy and tracking a lunar satellite during the day opens up a whole new world of possibilities. It means that ground control can know the exact position of satellites, landers, and rovers around the moon at any given moment. This ultra-precise navigation is essential for complex operations, like automated landings in tricky terrain or having robots and vehicles meet up and work together on the lunar surface. It provides a constant, reliable guidance system. For China, this is a huge step toward its ambitious space goals. The country has announced its plan to send astronauts to the moon by 2030 and to build an international lunar research station. A project of that scale requires the most advanced technology available, and reliable, all-weather day and night communication and navigation is at the top of the list. This successful daytime laser experiment proves that their technology is ready for the challenge. It's a key piece of the puzzle that will support their future crewed missions and ensure the safety of their astronauts. The benefits of this technology will extend to all kinds of deep space missions, not just those going to the moon. The same principles can be used to track spacecraft traveling to Mars and beyond, providing better data for course corrections and more precise orbital insertions. It will make our exploration of the solar system more accurate and efficient. Every future mission that needs to know exactly where it is in the vastness of space will benefit from the techniques proven in this experiment. It's a foundational technology that will help us push the boundaries of exploration even further. In the end, this daytime laser feat is a story of human ingenuity. It shows how we can develop clever solutions to overcome immense challenges, like the overwhelming power of our own star. By creating a beam of light so focused and a detector so sensitive, scientists have opened a new continuous line of communication with our nearest celestial neighbor. It's a bright signal that our journey back to the moon, and eventually beyond, is becoming safer, smarter, and more certain than ever before. It truly is a milestone moment for science and exploration. Consider it a giant leap for all humankind.